Good day, dear instructors. The topic of my project is self-supervised taxonomy expansion with position-enhanced graph neural network with application to Russian language. Taxonomy in my project is understood as the union of directed trees, also known as polyforest. Each edge from U to V in this graph denotes that V belongs to U, or equivalently, V is a part of U. Taxonomy enrichment task can be formulated as follows. Given an existing taxonomy and the set of new elements, find the set of new edges, which best describes the semantic relation between all the new elements. Most existing machine learning approaches focus on building the entire taxonomy from scratch, which is infeasible in many real-world applications, because the existing taxonomy should be preserved exactly. There exist some studies on expanding WordNet, in which the existing taxonomies are preserved, but the underlying approaches depend on the synset structure unique to WordNet, and thus cannot be easily generalized to other taxonomies. More recent works try to develop methodologies for expanding a generic taxonomy, however, most of them require external data for training. In contrast, the proposed algorithm requires no external data and explicitly models the local structure around each candidate position, which is expected to boost the quality of the expanded taxonomy. The proposed algorithm, called TaxoExpan, is self-supervised and uses graph neural networks to model the local structure around each node. Let me first describe a graph neural network. Each layer of GNN simultaneously updates representations of all the nodes in the taxonomy. Consider a single node U. Let n of U be the set of all parents and children of U, and U itself. The key layer of GNN transforms the node representation of U as indicated on the slide. Here alpha is the relative weight of node V with respect to the node U. There are two main types of GNN: graph convolutional network, which with constant weights for all the layers, and graph attention network, where weights are learnable and given by the formula on the slide. The formula on the previous slide describes a single-head graph attention network. It can be generalized to a multi-head case with the use of concatenation or mean aggregation between different heads, as indicated on the slide. In standard GNN, we do not model the influence of the relative position directly. However, it may be the case that, for instance, a parent of the node may have different contribution compared to the child. In order to capture this influence, it is proposed to add learnable position embedding layer in each GNN layer and augment a node representation with the position representation. In my project, I consider three possible positions: a parent, a child, and the node itself. The main aggregation formula of GNN will then be rewritten as shown on the slide. To obtain final node representation, we apply so-called readout operation with the learnable position importances. To measure how probable the node U is the parent of the node M, we use a log bilinear matching function, where the initial embedding of a potential child, fast text embedding in my case, is combined with the final embedding of a potential parent, as shown on the slide. To train the model, we use so-called info-NCE loss. Let M be some node in the existing taxonomy, and let U be one of the true parents of M. Assume we have n negative examples. These are nodes which are neither parents nor children of U, and n is hyperparameter. Then the loss for a single observation can be calculated as indicated on the slide. Note that this loss can be considered as cross-entropy of correctly choosing the true parent of the node M. After training to predict the parent for a test element X, we simply return an argument of the matching function maxima among the nodes in the existing taxonomy. We can also predict several candidates using the similar argument. In the practical part, I have re-implemented the algorithms from scratch using PyTorch geometric library. The public code provided by the authors was based on the deep graph library. To test the proposed algorithms, I used the data from the dialogue evaluation competition, which is actually the data from our first home assignment. The competition score is the F1 score between mean average precision and mean reciprocal rank. I used GNN with 3 layers in all the experiments. Other details are shown in the report and in the comments for my code. The competition baseline is quite simple but efficient. For each element from the test set, we calculate cosine distance to each element in the current taxonomy using fast text embeddings, and then take parents of 10 closest elements. As we can see, for nouns, all methods are well below the competition baseline. Moreover, more complex networks, namely graph attention networks, have worse results compared to less complex, namely a graph convolutional network. Similar results are for verbs. My experiments showed that network configurations which worked well on English language datasets failed on Russian language datasets. The further research in this area may consist of re-implementing some parts of the algorithm. Namely, we can consider different readout operations and or matching functions, as the article suggests. In this project, however, I used a particular variants of the algorithm, which were proved to be the most efficient for certain English language datasets, which were used in the experiments for the article. That's it. Thank you for attention.